I am Aritraj Chakraborty, lecturer in electrical engineering of Sri Ramakrishna Institute of Science and Technology. Today, I am going to solve some numerical problems related to DC motor. Now, this is the first numerical which I have to solve. We can see here the problem statement. A 250 volt DC shunt motor on no load runs at 1000 rpm and takes 5 ampere. The total armature and shunt field resistance are respectively 0.2 ohm and 250 ohm. Calculate the speed when loaded and taking a current of 50 ampere. If the armature reaction weakens the field by 3%. So what is the statement? You can see here a DC motor which is shunt wound. Supply voltage is 250 volt. Okay, the speed is 1000 rpm and takes total 5 ampere armature current. 5 ampere and current, and the total armature and shunt field resistance is 0.2 ohm, that is the armature resistance, and the shunt field resistance is 250 ohm. So we have to calculate the speed when it is loaded and taking a current of 50 ampere. At first it is taking 5 ampere current, and when it takes 50 ampere current, at that time we have to calculate the speed. And if armature reaction weakens the field by 3%, due to armature reaction, if the field weaks by 3%, we have to find out the speed. So the solution is here. You can see here, that is IL, that is the load current in first condition, that is 5 ampere. ISH, we know that ISH equals to VSH by RSH, and in case of shunt motor, VSH is equals to the terminal supply voltage, that is V. So that is ISH equals to V by RSH, that is 250 by 250 equals to 1 ampere. And IA1, that is the armature current, the value of the armature current at first condition, that is IL1 minus ISH. IL1 is, that is 5 ampere, the load current at first condition. So 5 minus 1 equals to 4 ampere. And now we have to calculate the value of EB or back EMF. So EB or E, that is the induced EMF in the armature, equals to, we know that V minus IA into RA. So here it is, V equals to 250 volt, IA equals to 4 ampere, RA equals to, that is the armature resistance, 0.2 ohm. So 4 into 0.2 equals to 249.2 volt. So that is the value of the induced EMF in the armature of the motor or the back EMF. So armature current on load, that is IA2, in second condition when it is loaded, that is IL2 minus ISH. ISH is constant because the shunt field resistance, that is 250 ohm, is always constant. So V, that is IA2 equals to IL2 minus ISH, that is 50 minus 1, that is 49 ampere. And now the value of E2, that means the induced EMF of the armature, that is EB or back EMF in second condition, that is E2, equals to V minus IA2 into RA, that is 250 minus 49.02. 02 is the 0.02 is the armature resistance, that is equals to 240.2 volt. So in second condition, the value of back EMF equals to 240.2. Now we know that the armature reaction weakens the field by 3%. So we can write here phi 2 equals to 0.97 of phi 1, because phi 2 is less than phi1, if the field is reduced by 3%, then the field flux is also reduced. That means the phi2 is the field flux at second condition, which is 3% lower than the field flux at the first time or first condition. So phi2 equals to 0.97 into phi1. 0.97 has come in account due to the less of 3% field. Then we know that N2 by N1 equals to E2 into phi1 by E1 into phi2. That is equals to 240.2 into phi1 by 249.2 into 9.97 into phi1. So N2 equals to 240.2 into 1000 by 249.2 into 0.97 equals to 993.69 rpm. So when the field current is weakened, that means when the field is weakened and when the armature current is increased from 5 ampere to 50 ampere, or when it is in loaded condition, so when the load current is increased, the load torque is also increased. For that very reason, the speed is reduced. We know that when the torque is increased, then the speed is reduced. So at first the speed is 1000 rpm, and in second condition the speed is 993.69 rpm. Okay, so that is the first problem or numerical number 1. Now we have to discuss about the numerical number 2. That we know, and here we can see that a 250 volt DC shunt motor having an armature resistance of 0.25 ohm carries an armature current of 50 ampere, runs at 750 rpm. If the flux is reduced by 10%, find the speed. Assume that the load torque remain the same. Okay, so here the supply voltage equals to 250 volt. IA1, that means the armature current at first condition, that is 50 ampere. RA is the armature resistance, that is 0.25 ohm. N1, that means the speed in first condition, that is 750 rpm. We can see there, that is 750 rpm. And the back EMF, that is E1, equals to V minus IA1 into RA. So V equals to, we know that 250 volt minus IA equals to 50 into, that is RA equals to 0.25. So E1 or the back EMF in first condition, that is equals to 237.5 volt. That is the first condition. In second condition, the flux is reduced by 10%. So condition after reducing the flux, we know that phi2 equals to 0.9 into phi1, because it is less 20% of the first condition flux, that is phi1. So phi2 equals to 0.9 into phi1. And load torque, we know that from the torque equation, that is T or torque proportional to flux into armature current, that is phi Ia. Since the load torque remains the same, then we can write that T2 is the torque in second condition, and T1 is the torque at first condition, that is T2 equals to T1. So we can write here that phi2 into Ia2, that is phi Ia. So phi2 into Ia2 equals to phi1 into Ia1, because these torque are equal. Okay, according to the question, assume the load torque remains the same. So Ia1 equals to phi1 by phi2 into Ia2. Sorry, Ia2 equals to phi1 by phi2 into Ia1. Okay, then equals to here Ia1, we know that relation phi2 equals to 0.9 into phi1. So that is equals to, we can write that IA equals to, or IA1 equals to 50 ampere. So 50 by 0.9, because this ratio is 1 by 0.9. okay, so that is by 0.9 equals to 55.56 ampere. That is the value of IA2, and from there we can write the value of E2, or the value of the back EMF in second condition, that is V minus IA into IA2 into RA. So V equals to 50, IA2 that is 55.56, means we can write that 55.6 into 0.25, that is the armature resistance, equals to 236.1 volt. So that is the value of E2. E2 means the back EMF in secondary condition. And from there, from this equation, N2 by N1 equals to E2 phi 1 by E1 phi 2. We can solve the value of N2. So N2 equals to E2 into phi 1 by E1 into phi 2 into N1. So E2, the value of E2 is 236.1, and the value of N1 is, we can know that 750 rpm. So 236.1 into 750 by the value of E1 is, the value of E1, that is the value of E1 is 237.5. So 237.5 into phi 1 by phi 2 means 1 by 0.9. So 237.5 into 0.9, it is equals to 828 or 828.5 rpm. So that is the value of the speed of the motor, of the DC shunt motor in the second condition. Okay, so that's all. That is the numerical number 2. Now the next one is the numerical number 3. So here we can see the problem, that is a 240 volt DC series motor. So in previous two solution or numerical solution, we can see that these are about DC shunt motor, but right now we are going to solve a numerical of DC series motor. A 240 volt DC series motor takes 40 ampere when given its rated output at 1500 rpm. Its resistance is 0.3 ohm. Calculate the value of the resistance that must be added to obtain the rated torque A at starting, and that is, we have to find out the rated torque A at starting and B at 1000 rpm. Okay, so DC series motor means it has a high starting torque. Okay, so at first we have to write down the given datas. So here the given datas are the rated current, that is you can see here I equals to, it is series motor, so the armature current and supply current is same, because the armature current is directly supplied or directly supplied to the armature winding from the source. Okay, so I equals to IA equals to 40 ampere, voltage V equals to 240 volt, and the N1 means the speed of the motor in first condition, that is equals to 1500 rpm, and the value of the armature resistance, that is RA. So value of the armature resistance, that is RA, equals to 0.3 ohm. N1 equals to 1500 rpm. So from here we can find out the value of E or back EMF, that is equals to V minus IARA. E equals to, so V is the 240 volt, IA is 40 ampere, RA is 0.3. Okay, so 240 minus 40 into 0.3 equals to 228 volt. So that is the value of back EMF. So now we have to find out the rated torque. Calculate the value of resistance that must be added to obtain the rated torque. So the value of resistance we have to find out. So at starting the back EMF is 0. We know that when the motor is at standstill condition, then the conductor or the armature is not in rotating condition. That means when it is in static condition, no conductor cuts the magnetic flux, so there is no EMF is induced in the armature, so back EMF is 0. Okay. In order to obtain the rated torque at rated current, an additional resistance R1 is connected in series with the armature. So the value of, we have to find out the value of the R1. So E1 equals to V minus IA into RA plus R1. So when it is in standstill mode, then the value of E equals to 0. Okay. So V equals to 240 minus 40 into 0.3 plus R1. R1 is that resistance we have to find out. So the value of R1 equals to 240 minus 12 by 40 equals to 5.7 ohm. Okay. And when the motor is running at 1000 rpm, we have to find out the value of the armature resistance. So at that condition, let R2 be the resistance connected in series with the armature to obtain the rated torque at the speed of 1000 rpm. So E2 equals to V minus IA into RA plus R2. Okay. So with the value of V equals to 240 volt minus 40 into 0.3 plus R2 equals to 228 minus 40. Okay. So now we have to find into R2. We don't know the value of R2. Okay. From this equation, from that equation, if we know the value of the RPM, that is 1000 RPM, we can write here that N2 into phi 2 by N into phi or N1 into phi 1 same equals to E2 by E. So N2 into, we know that in case of series motor, phi proportional to IA. That means the flux is proportional to the armature current. So instead of phi 2, we can write here IA2 by NIA, N2 into IA2 by N into IA, or N1 into IA. N1 is the first speed, that is the 750. In case of that is the 1500 rpm. Okay, in first condition the value of speed is 1500 rpm. So now N2 into IA2 by N into IA, okay, or N1 into IA1 equals to E2 by E. So since we know that IA2 equals to IA, because the armature current is always same, that is 40 ampere. Okay, so N2 by N equals to E2 by E. So N2 equals to 1000 and N equals to 1500. E2 equals to, you know that E2, the value of E2 is 228 minus 40 into R2. So 228 minus 40 into R2 by 228, which is the value of E. Okay, so that is the value of E, 228 volt. So R2 equals to 1.9 ohm. So from there we can find out the value of R2, that is 1.9 ohm. Now the next numerical, that is the numerical number 4. Same as the previous one, it is also about the DC series motor. So here you can see a series motor with an unsaturated magnetic circuit. Unsaturated means when the field is not saturated. That is, the maximum number of flux, if it is not produced in the field, we can write that unsaturated magnetic circuit. And 0.5 ohm is the total resistance when running at a certain speed, taking 60 ampere at 500 volt. If the load torque varies as the cube of the speed, calculate the resistance required to reduce the speed by 25%. Okay, so if the load torque varies as the cube of the speed, we have to calculate the resistance required to reduce the speed by 25%. So here E1 is the EMF or back EMF equals to V minus IA into RA. So from the question we can see here the value of voltage, or V equals to 500 volt, and IA equals to, here is that 60 ampere, and RA equals to 0.5. So 500 minus 60 into 0.5 equals to 470 volt is the value of back EMF, and the speed is reduced by 25% in second condition, that means in N2 condition. So N2 equals to, we can write that 0.75 into N1, okay, because it is reduced by 25%, so 100 minus 25, that is 75% of N1, okay. And according to this equation, the load torque varies as the cube of the speed. So the load torque T proportional to N cube, N is the speed, so T2 by T1 equals to N2 by N1 cube, okay, equals to, that is N2 by N1. N2 by N1 means 0.75 into by 0.75 to the power 3 or 0.75 cube according to this relation. And we also know that according to torque equation, T proportional to phi into Ia. So T2 by T1 equals to phi 2 into Ia2 by phi 1 into Ia1. So, and we also know that phi proportional to Ia in case of series motor. So T proportional to Ia square. So instead of phi 2 Ia2, we can write that is Ia2 square, and instead of phi 1 Ia1 equals to, we write that Ia1 square. So Ia2 square by Ia1 square equals to, we can write down that N2 by N1 cube from this equation, N2 by N1 cube, okay. So now the value of Ia1, here it is, the value of Ia1 is 60 ampere. So Ia2 square by 60 square equals to 0.75 cube. And now, so Ia2 equals to 60 root, so that is 60 into root over 0.75 cube, okay. So that is equals to 38.97 ampere. So the value of the secondary condition current, that is Ia2, equals to 38.97 ampere. So let R be the additional resistance to be connected in series with the armature. That is, we know that E2 equals to V minus Ia2 into RA plus this R, which have to connect it in series, the additional resistance. So 500 minus 38.97, the value of armature resistance is 0.5 plus R. So E2 equals to 480.5 minus 38.97 into R, okay. And we know the speed equation, E2 by U1 equals to N2 phi 2 into N1 phi 1, or in case of series motor, phi proportional to I. So N2 into IA2 by N1 into IA1. Okay, so that is equals to 480.5 minus 38.97. 480.5 is the value of E1. Okay, and E2, the value of E2 equals to this 480.5 minus 38.97 are, that is the value of E2. Okay, and the value of E1 is the value of E1 is 470 volt. So E2 by E1, that means 480.5 minus 38.97 R by 470 equals to 0.75 into 38.97, okay, by 60. This 38.97 is the IA2 and 60 is the value of IA1 or armature current at the first condition, and 38.97 ampere, that is the value of armature current in second condition, into 0.75. So 0.75 is the value of the speed which is reduced. Okay, so from that equation we can write down here that R equals to 6.455 ohm. Okay, so that is the numerical number 4. And that is the last one, the numerical number 5. So here you can see that a 500 volt shunt motor, here it is also the problems of shunt motor, takes 4 ampere on no load. The armature resistance including that of brushes is 0.2 ohm and the field current is 1 ampere. Estimate the output and the efficiency when the input current is in A condition, that is 20 ampere, in B condition, that is 100 ampere. So we know that constant loss equals to no load power input minus no load power copper losses. Okay, constant loss means the value of iron loss, that is, we can write here PC, that is the constant loss, equals to no load power input, that is V equal into I0. So what is the value of I0? I0 means the no load current minus the no load copper loss, that is I square R loss, IA square R loss. So IA square R loss means, IA means the copper loss of armature actually, because the shunt field loss is not taking account. So that is I0 is the total current, total supply current. So IA means I0 minus ISH, because ISH, the value of ISH is very small. So the main loss is the armature copper loss. So I0 minus ISH square, that is equals to that IA. So into RA equals to 500, that is the supply voltage of motor, into 4, that is the value of no load current or supply no load current, minus 4 minus 1 in bracket 4 minus 1. 4 minus 1 means the value of supply current 4 and the field current is 1. So the value of armature current is 3. 4 minus 1. So 4 minus 1 square into 0.2, that is the value of RA, armature resistance, equals to 1998.2 watt. Okay, so that is in first condition. Now in case of second condition, when the value of the input current is 20 ampere, the power input equals to V into I, that is 50 into 20, that is the 10,000 watt, and armature copper loss is equals to IA square RA, that is I minus ISH square. I is 20 in according to this condition, Okay, 20 minus 1 square into 0.2, that is 72.2 watt. That is the armature copper loss. And total loss means the value of iron loss plus copper loss. We know the value of iron loss is always constant, so that is the value of iron loss, 1998.2 watt. So the value of armature total loss is because the copper loss plus iron loss. So the value of copper loss is 72.2 into 1998.2 equals to 2070.4 watt. That is the total value of the total loss at armature current of A. At the value of supply current of 20 ampere, the total losses is 2070.4 watt. And the efficiency of motor in that condition, input minus, we know that efficiency equals to input minus losses by input, or output by input. Output means input minus losses. So the input is the 10,000, that is the 10,000 watt power input. Losses is 2070.4 watt by 10,000 equals to 0.793 per unit, or in percentage that is 79.3%. Okay, that is for 20 ampere supply current condition. And in 100 ampere supply current condition, the power input is 500 into 100, that means 50,000 watt. And copper loss equals to same as I minus IC square into RA. So 100 minus 1 square, that is 99 square into 0.2, that is equals to 1960 watt. And total losses, we have to find out the total losses. So before find out the total losses, we have to find out the armature copper loss. So armature copper loss, that is 1960 watt. So total losses is PC plus armature copper loss. PC means the constant loss, we know that is 1998.2 watt. So total losses is 1998.2 plus 1960, that is equals to 3958.2 watt. Okay, in that condition, efficiency equals to input minus losses by input, that is 50,000 minus 3958.2 by 50,000 equals to 0.91. This 0.91 is the per unit. Okay, per unit efficiency. So if it is calculated in percentage efficiency, so we have to write 92.1% instead of 0.921. Okay, so that's all. Thank you.